Okay, so in the previous class we discussed about the failure criteria. So what are different failure? What are different ways of failure? So in that we discussed one kind of failure is if there are excessive deflections or deformations. So we can treat that one as a failure. And in some materials, we'll take yield strength as the failure criteria. In case of brittle materials, we'll take the ultimate strength as the failure criteria. In some instances where components are rubbing against each other, so we need to consider bearing pressure as also a failure criteria and also wear as a failure criteria. So now, once you understand how to characterize the load, then how to estimate the load, then you define the failure criteria. Next we'll move on to the next topic, which is what is the calculation of the allowable stress based on this factor of safety. So first we'll define what is factor of safety, then what are various factors which will influence the choice of this factor of safety, then we'll see how to calculate these allowable stresses. Then after that we'll go for the design of a component. First we'll take up a simple loads, then we'll go for the complex loading. So now first we'll see the what is the definition for this factor of safety. So factor of safety is defined as, or it is a measure of reserve strength provided to take care of any unexpected or unpredicted conditions that may arise due to uncertainties in the properties of the material or magnitude and direction of the load and operating conditions. So that means, so this factor of safety is nothing but it is a reserve factor which is applied in the design so as to take care of whenever there is an unexpected or unpredicted conditions with respect to properties of the material. So generally the design engineer will assume that while designing the component, he will assume that the material is homogeneous. So it is not possible for the designer to predict whether there is any defects in the material or not. So therefore, generally while designing it, designer engineer will assume that the material is uniform or homogeneous, and also will estimate the loads. So based on the given conditions, sometimes each estimation may not accurate, maybe because of there may be change in the some operating conditions. So therefore, to accommodate all these variations or fluctuations in the conditions, so we need to provide a reserve strength. That reserve strength is provided in the form of a factor of safety. So now, how this factor of safety and what factors this factor of safety will depend. So like we already mentioned here, so if this reserve strength is provided to care of uncertainties or unexpected conditions, operating conditions. So in those conditions, we need to take the factor of safety. Always, all design engineers will follow the factor of safety, but only thing is what is the value of the factor of safety. So that again depends upon the conditions. So value of the factor of safety depends upon, the first one is effect of failure. So that means, so if failure happen, what is the level of severity in that failure? What is the cost or danger involved in the failure? So that means, suppose if the designer engineer designing for a bearing of some bearing of a shaft. So now here if this bearing is failed, then even if the bearing is failed, the severity of the failure is not going to be that much. So it is not going to damage any surrounding atmosphere or surroundings. It is not going to create any kind of failure if a bearing in the shaft is fails, or similarly bearing in a gearbox fails. So it is not going to be a big deal, or there would be much lost in the time. You can easily replace that bearings and then you can start production again. So or you can start using that component. That means there may be low damage to the cost or less danger is involved. So in such situations, so generally the design engineer will consider only a low factor of safety. Or else while designing something like a nuclear reactor or some pressure vessel, so a boiler. So if you take pressure vessel or a nuclear reactor or a boiler, if that fails, then what happens? I think recently we have seen one incident in Vizag also, Visakhapatnam. There the chemical pressure vessel is blasted because of some unknown reasons. So maybe those are the different things, but it is failed. So because of that failure, there is a lot of loss of human life is there, and also there may be some cost, and also people are died in that accident. So if that is the severity of the accident, then in that case, if that designer is designing component for that kind of environment, that means whenever he is designing pressure vessels or maybe a critical components, it need not be a pressure vessels. I given just one example that. So whenever, if the failure of that component takes place, if the failure results in very severity or maybe loss of human life, so then in such cases, so the factor of safety is going to be the higher value. So that means, see, the designer engineer has to consider this point. So what is, if failure happens, what happens? So that point he has to take care. So based on that, he will choose the factor of safety. Suppose if there is no severity or no damage or no cost, not much cost is involved because of failure, generally low factor of safety is considered for the design. If the severity of the damage is used, then always, so designer engineer will look at it at any cost that it is not going to fail. So like that, if that is the case, the factor of safety is going to be the higher value. So therefore, this is one of the important point while choosing the factor of safety, a design engineer has to consider. Then type of load. So we already discussed. So we have static loads. We may have dynamic loads when a machine component is put into under operation. It may subjected to either static load or dynamic load. So if the load is static, so because it is not going to change with respect to time, so then we can take that, we can assume a less factor of safety, because the static nature of the load, it is not going to be deviate from the original conditions not much. So therefore, the factor of safety for designing against the static load is going to be small when compared to design against the dynamic load. So here this dynamic load is going to be changed both in magnitude as well as direction with respect to time. So therefore, lot of uncertainty is there in this case, in case of dynamic loads. So the factor of safety value should be higher when compared to the static loading. So this is the second one. Then next, accuracy of the load calculations. So like I mentioned here, so if the prediction or the calculation of the loads is not done accurately, then again we need to take higher factor of safety. If it is, the calculations are most accurate, then lower factor of safety is sufficient. If the accuracy is not good, so one has to consider higher factor of safety to avoid failure of the component. Then material selected. So like depending upon the type of material is selecting for the design, again this factor of safety will depend. Suppose if a ductile material is designed, so now this ductile material will give some warning before failure. So that means, so yielding will take place in case of ductile material. That yielding is nothing but it is an indication of failure. So that means it will give you, it will trigger a signal to the engineer showing that the component is going to fail. So whereas if you take a brittle materials, it won't show any signal, it won't give you any signal, or it won't show any considerable plastic deformation. Suddenly these are going to fail. Brittle materials are going to fail suddenly without giving any indication. Whereas ductile materials will give you some indication. So therefore, so while designing the component based on the material, if the material is brittle, the factor of safety should be higher when compared to the ductile materials. Similarly, if the material is not homogeneous, like I mentioned in the beginning, if it is not homogeneous, if there is a chance of more number of defects or impurities in the material, then the factor of safety should be higher. Because of impurities or defects, the strength of materials will decrease. So now, if you estimate the loads and stress values based on homogeneity, it is going to fail under the given conditions. So therefore, if there are any impurities or non-homogeneity is present in the material of the component, then the factor of safety should be higher. So when compared to for a homogeneous material. The next one is the reliability. desired reliability. So the I said is, so if I design a component, if I want to have 100% reliability, that means whatever may be the operating conditions, so whatever may be the loads, so when it is subjected to, when it is put into operation. So if it is 100%, if I want to have a 100% reliability, that means the component should not fail. Whatever may be the load it is acting on the component, and whatever may be the, whether the load may be the static or dynamic, or whatever may be the operating conditions also. So now if I want to have 100% reliability, that means the component should not fail. In that case, I need to go for higher factor of safety. But in practice, we cannot take every component is having 100% reliability. If you want to use 100% reliability, then you need to consider higher factor of safety. With higher factor of safety, what happens is, again, there may be some problems are there. So if the factor of safety is very high, the size of the component will increase, will become very large. So if the size of the component is very large, then obviously the cost of the component will increase, everything will increase, other costs will also increase. So therefore, always the designer engineer has to make a balance between this reliability and also the size or the factor of safety. You need to choose this factor of safety appropriately so that you can minimize the cost, and at the same time the component should have the desired reliability. Then next one, service conditions. So that is whether the component is operating in the normal environment conditions, or if there is any corrosive environment is there, or maybe if there is any changes in the atmospheric conditions also. So based on all these conditions also, the factor of safety will depend. Suppose if the environment is corrosive, then the component will get affected by this corrosive environment, and its life is going to decrease day by day. So because of this corrosion, and it is going to fail. So in that case, maybe the higher factor of safety need to be considered when the component is operating in a corrosive environment. Similarly, when there is a fluctuations in the temperatures, because of these fluctuations, the component temperature fluctuations, the component may subjected to a thermal load, which is again fatigue in nature. So because of this temperature fluctuations, so the component life will decrease drastically. So therefore, in order to have certain reliable life to the system or to the component, so the factor of safety should be higher even in this case when compared to the normal working conditions or normal operating conditions. Then you have the manufacturing quality. So this is also one more important thing. So when manufacturing a component, so generally the design engineer will design the components for a good quality. So that means the surface finish of the component should be good. Or not only that, the desired dimensions also should be accurate. So if the design engineer is designed for one dimension, but it is not possible for that for the manufacturing facility to produce to the exact desired dimensions, then there is a deviation from the design calculations. So in that case also, the design engineer need to provide a factor of safety to accommodate these variations in the dimensions of the component. So not only that, the quality of the machining, if the machining is taking place on the component, so the quality of the machining is also or it may be also one of the important factor while choosing the factor of safety. If it is a rough surfaces are created because of the manufacturing process, so whenever there is a rough surfaces, obviously it is subjected to the friction. Not only friction, because of rough surface, there may be a chance of defective in the component. When it is subjected, that component is subjected to the certain loading conditions, these cracks will grow and propagate from one location to other location, and the component may may fracture also. So to avoid that, so here to arrest that crack propagation, whatever it may be, so that the factor of safety should be very high in these conditions. And also not only that, he has to make sure that he has to take the cost is also into the effect. Like I mentioned here, for a component, if you take higher factor of safety, then what happens is the size of the component will become large. Once the size increase means the material cost will increase. Not only that, the manufacturing cost will also increases, and everything, the transportation facilities and also maintenance cost of the component will also increase. So all the costs associated with the component will go on increasing if you use higher factor of safety. So therefore, while taking that factor is also into consideration, one has to select this factor of safety appropriately. It should not be too high or it should not be too low. If it is too high, the costs goes on increasing. If it is too low, the component may fail. So there should be one has to strike a balance between these two. So it should not fail. That means it should have at least some acceptable reliability, and at the same time the cost should be within the acceptable levels. So by striking a balance between these two, then the factor of safety will be decided. So once the factor of safety is decided, then we can calculate the allowable stresses in any component. So now I'll show that in the next slide. So depending upon the criteria of failure decided, the strength of the material is divided by the factor of safety to obtain the allowable stress or design stress. So here the definition for this allowable stress, sometimes we'll call it as working stress also. Allowable stress or working stress, or sometimes this is also called design stress. So all these names are same. Allowable stress, working stress, or design stress. So here this allowable stress here it is written allowable stress or design stress is given. Sometimes we'll call it as working stress also. So working stress is nothing but it is defined as a ratio of strength of material divided by the factor of safety. So now we are saying based on different factors, the factor of safety can be decided. So once this factor of safety is decided, then the allowable stress will be calculated by taking the strength of the material and dividing the strength of material by this factor of safety, you will get the allowable stress. Now, once you calculate the allowable stress, if that allowable stress is less than the individual stress or the individual stress is more than this allowable stress, the component is going to fail. Otherwise, the component is going to be safe. That is the design criteria. Here the design criteria is, so first we need to calculate the allowable stress or design stress or working stress, whatever it may be. So then if you compare the value of the allowable stress to the actual stress induced in the component when it is put into operation. That means we know what are the loads when the component is put into operation, it is subjected to some kinds of loads. So because of loads, we need to compute what is the stress in the component. So now we'll take the stress value and we'll compare the stress value with respect to this allowable stress. So now if the individual stress, that stress which is induced because of the applied load on the component, we'll call it as the individual stress. If that individual stress value is less than this allowable stress, we can say that the component is safe. Or if it is more than or equal to that, the component is going to fail. So therefore, always we need to design any component such that the individual stresses should be less than the allowable stresses. So now to compute this allowable stresses, I already told you, it is nothing but the strength of the material divided by the factor of safety. So now again different criteria are there for different materials. Like if you have a ductile material, the strength what we are considering for the failure is, I think I will ask your response. So we discussed that also. I don't know how many of you are following the class. Just I'll test that now. So now I'll come to here. So now, okay. So first anybody can tell. So what is the strength need to be considered for the failure in case of ductile materials? So, ఈరోజు వచ్చాడు ఈడు బంగారు శివప్రసాద్, మిస్టర్ శివప్రసాద్
సార్.
ఏంటమ్మా ఈరోజు క్లాస్కి వచ్చావు? ఏమయ్యా ఇన్ని రోజులు?
ఫోన్ లేదు సార్.
ఫోన్ లేదా?
సార్
ఈరోజు కొత్త ఫోన్ కొన్నావా?
కొత్త ఫోన్ కొన్నాను. కొత్త ఫోన్ కొన్నాను సార్.
ఓకే, మరి ఈ రోజు నుంచి రోజు అటెండ్ అవుతావు అయితే?
సరే.
అవుతావా?
అవుతాను సార్, రోజు అటెండ్.
ఓకే, రైట్. Right. So I think somebody has put in the answer in the comment box. Okay, I will ask this Lokesh. Lokesh, are you there? 317. జస్ట్ ఓకే జాయిన్ అయ్యి ఎక్కడ ఉన్నట్టు ఏదో లాభాలో ఉన్నట్టు. Hey, 317, are you there or not? Just you switch on your mic and then speak. I want to know whether you are present right now or not. 317. Boda Lokesh. I think he is not there. So, okay, right. So, next one. So then what is the necessity of, I'll remove him from the class so that he will not attend the class from next time onwards. It's not required also. Why he is joining without following the class, just logging and sleeping somewhere else. Then 315.
Sir.
Okay. So what is the criteria we follow for ductile materials as a failure strength?
Sir, ductile material అనేది yield strength reach
Yield
అయితే
strength is the criteria for failure in case of ductile material, right? So,
Yes,
but
sir.
in case of brittle materials,
ultimate tensile strength.
okay, very good. So, okay, right. So I'll go to the another fellow. So I think Vijay Babu 23. So I'm checking randomly whether they are present or not also. Not only asking the question, that is not the purpose. Just I'm checking. That fellow is not there, na? Earlier. So like this, I'm checking randomly. 23. Okay, he is there. I think I am assuming. I don't know whether he is following or not. I'll assume that he is following. So then, if he answers the question, we can concretely say that okay, he is following the classes. So earlier person has told that in case of brittle materials, yield strength is ultimate strength is the criteria. Is it right?
Yes, sir.
Huh?
Yes, sir.
So again, in ultimate strength, you need to consider ultimate tensile strength or ultimate compressive strength.
Ultimate tensile strength, sir.
Why you need to take ultimate tensile strength only? Why not compressive strength?
Really, sir.
Really? Okay, right. So you follow the class. In meantime, you will understand that. Next, I'll go to roll number 30. Ganta.
Sir.
Okay, so I think you are there, right? So what is the, like I asked the same question previous one, that is 23 Nadia. So ultimate strength tensile, ultimate compressive strength. Which one we need to take it as a failure criteria in case of brittle materials?
Tensile, sir. Ultimate tensile.
Same. 23 అని చెప్పాడు, నువ్వు అదే చెప్తాను అంతేనా?
Sir.
రాంగ్ అని చెప్పా కదా అక్కడ, మళ్ళీ అది ఎందుకు చెప్తున్నావు? So why you have to take only ultimate tensile strength? Why not ultimate compressive strength? No idea. Huh? Okay.
It is, sir.
Okay. So next I'll go to 355. Okay. So నీకు తెలుసా అమ్మా?
అల్టిమేట్ టెన్సైల్ స్ట్రెంత్ అనుకున్నాను. అల్టిమేట్ టెన్సైల్ స్ట్రెంత్ అనుకున్నాను.
అంతే అనుకుంటున్నా, కానీ అది ఎందుకో అదే ఎందుకో అని తెలుసా? రీజన్ ఏమని తెలుసా? ఓకే, నో ప్రాబ్లం, నో ఇష్యూ. సో ఐ థింక్ యు ఆర్ ఫాలోయింగ్ ద క్లాస్ రెగ్యులర్. అంతేనా? క్లాస్ కంటిన్యూస్గా అటెండ్ అవుతామా? మధ్యలో లాగిన్ అయిపోయి ఫోన్ పక్కన పెట్టేసి వేరే యాక్టివిటీస్ ఇన్వాల్వ్ అవుతున్నావా? ఫాలో అవుతున్నా కంటిన్యూస్ క్లాస్ని? ఎన్నింటికి జాయిన్ అయ్యావు క్లాస్కి ఈరోజు? 9:15 జాయిన్ అయ్యావు. అటెండెన్స్ ఇచ్చావు నువ్వు అయితే? ఓకే, వెరీ గుడ్. So next I'll move on to roll number. I think somebody is commented here, so I'll exclude him. 310. LE10.
Sir.
Okay. No, Hemlata. Okay, right amma. Neeku telusa emana? Idea unda?
Sir.
No idea. So follow అవుతున్నా రెగ్యులర్ క్లాస్?
అవుతున్నాను సార్.
అర్థమవుతుందో చెప్పేది?
అర్థమవుతుంది సార్.
ఓకే, రైట్. So I'll go on to LE3. Okay, heroes got raledadu. Okay, no issue. LE7.
Yes, sir.
So do you have any idea? I think మీరు డిప్లొమా ఆల్రెడీ చదివి ఉంటారు కదా.
Yes, sir.
ఏంటి అల్టిమేట్ స్ట్రెంత్ ఎంత, అల్టిమేట్ కంప్రెసివ్ స్ట్రెంత్ తీసుకోవాల్సింది?
అది మనం లోడ్ ఎలా పడుతుందో దాన్ని బేస్ చేసుకుని తీసుకుంటాం సార్.
లోడ్ ఎలా పడుతుందో దాన్ని బేస్ చేసుకుని. దట్ మీన్స్ వాట్ యూ వాంట్ టు సే ఇస్, if the load is tensile load, you have to take tensile strength. If the load is compressive, you have to take compressive strength, right?
Yes, sir.
Okay, very good, right? Okay, so okay, that is the answer. So don't say that only ultimate tensile strength you need to take. Suppose if the component is subjected to a compressive load, then it is subjected to a compressive stress. In that case, you need to take ultimate compressive strength only. So when the load is subjected to tensile strength, tensile load, so then the component will subjected to a tensile stress, then the criteria should be tensile strength. So for most of the materials, so if I say ductile materials, yield strength in tension, yield strength in compression is same for most of the materials, not all the materials. I'm saying that for most of the materials, yield strength in tension is same as yield strength in compression. So that's why simply we say yield strength. Yield strength is nothing but it may be a tensile strength or it may be a compressive strength also. Whereas in case of brittle materials, especially since ultimate strength is the criteria for the design of the brittle materials, in case of brittle materials, the ultimate strength in tension is not equal to the ultimate strength in the compression. So generally, ultimate strength in compression is having higher value when compared to the ultimate strength in tension. So therefore, based on the load, then you need to consider whether you need to consider the compressive strength or tensile strength. In case of brittle materials, in case of ductile materials, like I mentioned, tensile strength, tensile yield strength or compressive yield strength is almost all same. So that's why we don't follow any distinction there. Of course, if required, we need to follow. If it is deviating, those two strengths are deviating largely, then we need to consider there also. If it is a tensile load, tensile stress, you need to take tensile yield strength. If it is a compressive load, you need to take compressive yield strength. So like that we need to consider. So don't think that always you have to take only tensile strength for all the cases, sir. Right? Okay. So I'll move on to the presentation again. Right. So that's what he said. So now the criteria for ductile material is yield strength is the criteria. So now since we are providing some factor of safety, that means we are reserving some strength out of this ultimate yield strength. We are providing some reserve strength. So the reserve strength, what we need to do is we need to reserve strength means we are reducing the strength of the component. Actual strength is SY, that is the yield strength. But if I divide factor of safety, always factor of safety, mind you, the minimum value for factor of safety is 1. Always it is 1 or more than 1. Minimum value for the factor of safety is 1 means. So this strength is going to, if you apply factor of safety, what happens is the strength may be either it is same. If factor of safety is 1, it is going to be SY only. Or if the factor of safety is increasing from 1, what happened to the strength of the material? We are decreasing the strength of the material, even though its strength is SY. So if let us say if I take a factor of safety of 2, then what is the allowable stress, or what is the allowable stress? Now it will become SY by 2. That means I reduce the strength of the material to half. So now the strength of the material will become 0.5 SY. So then that means we are reducing it, means we are reducing it to half, means remaining half we are taking it as a reserve strength. That means only we are stressing the 50% of the strength, remaining 50% of strength we are taking it as a reserve strength. So therefore allowable stress can be calculated as yield strength divided by the factor of safety. So in short notation, factor of safety is denoted by something like this. Fs within the brackets will follow this kind of notation for this factor of safety. So similarly, if it is a ductile material, so brittle material, SUT divided by Fs. So that is ultimate tensile strength or ultimate compressive strength divided by the factor of safety will give you the allowable stress for brittle materials. So now once we know this allowable stress, how to compute the allowable stress, then we need to check whether the design is safe or not. How we can check that is, you will need to take this allowable stress value and you need to compare this allowable stress value to the individual stress value. So then if you compare that, so if they are equal or this allowable individual stress is less than this allowable stress, we can say that the design is safe. Or else, already if you want to design for the design, you need to design the component, then what you need to do is, you need to equate this allowable stress to the individual stress. So based on that, you can calculate the dimensions of the component. So that's what written here. Which is here, this design stress is used to determine the dimensions of the component. That means we'll take this allowable stress value and we'll equate this one to the individual stress value. Then based on that equation, we'll find the dimensions of the component. Okay, this is how design can be carried out. So now we'll see different cases. So just now I told we calculated the allowable stress. Next case is how I can compute the individual stresses also. Then only I can compare and then I can design the component. So now for that we'll see what are various types of stresses. What is the definition? I think you already studied these things in your previous courses, mechanics of materials or mechanics of solids course. Again, but still, just we'll take some kind of review of all those stresses. Then how we can apply these design principles to design the component also, we'll see that. So in that, first we'll take simple stresses. So that is, in case of simple stress means there is only one kind of stress. Then you have a complex stress. Complex stress means if there are more than one kind of stress. So simple in the sense, so generally we have different types of stresses, that is normal stress, shear stress, similarly bearing stress. We already discussed those in previous slides. Our previous classes we already discussed about those things. So when a beam is subjected to bending moment, you will get a bending stress. When a shaft is subjected to a twisting moment, you will get a shear stress. When a bar or a beam or whatever it may be rod, if it is subjected to a tensile load, it is subjected to only tensile load. So that means if there is only one kind of stress, that is only normal stress or only shear stress or only bending stress or something like that, then we call them as a simple stresses. If there are combination of stresses, I have both bending stress as well as shear stress, then I can call that one as a complex stress system. So now we'll move to we'll consider that complex system later. Now we see in case of simple stresses how we can compute the stress values. That is the thing. So in that, first we'll consider the normal stress. So here you can say when the mechanical component is subjected to an external load, a resisting force is set up within the component. This resisting force per unit area of the component is called stress. This is the definition of the stress. I think all of you know about this, so I'm not going to explain that again. So then the maximum stress developed in the member should not exceed the allowable value as obtained from the material strength considering certain value of factor of safety. That is, any stress should always be less than your allowable stress. Limiting values of dimensions desired can be calculated by equating sigma to sigma allowable. So if this notation, sigma within the bracket, will take it as a sigma allowable. So then if always what we discussed in the previous slide, again the same thing comes here. If the sigma is equal to sigma allowable, then based on that we can calculate the dimensions of the component. So always, so your sigma should be less than this allowable sigma value. So then only your design is safe. So equation sigma is equal to sigma allowable is called design equation, and it is used for simple stresses. Only this is the criteria followed for in case of only simple stresses. That means if there is only one kind of stress is there, we follow this equation as a design equation. So in that case, so first kind of simple stress we can say direct tensile or direct compressive stress. So we know when a component which is subjected to a tensile force like this here it is shown, or a compressive force it is subjected to something like this, we know the formula for this. So here tensile and compressive stress will consider it as a normal stresses. So because of tensile stress, the specimen length will increase, or because of compressive stress, the component length will goes on decreasing. So this is the criteria. When the length is increasing, we'll call it as a tensile. When the length is decreasing, we'll call it as a compressive. So in both the cases, whether it is a tensile stress or a compressive stress, both are normal stresses only, and the magnitude of stress is divided by load by area. So now what you need to consider is what is the load applied. So in this diagram, the load applied is P. Then the resisting area, here you need to consider load divided by the resisting area, we'll call it as a stress. So you need to consider the normal resisting area. So normal means perpendicular to this load, the area which is perpendicular to this load. So therefore this is the area. Here that resistance will produce, that we denote it as sigma T. Tensile stress is denoted by sigma T. Tensile normal stress, you can say it is sigma T, and sigma C is nothing but normal compressive stress is denoted by sigma C. So now here also the formula remains same, only here it is P by A, here is also P by A. Tensile stress will take it as a positive stress, compressive stress will consider it as a negative stress. So now the design equation for simple tensile stress is nothing but this one. Your sigma T should be less than or equal to your allowable sigma value. So this allowable sigma value will come from your strength of the material. That is, if it is a ductile material, your sigma allowable is nothing but yield strength divided by the factor of safety. So if you consider factor of safety as 1, simply you need to consider it as a yield strength. Similarly, in case of compressive stress, so if the component is subjected to a compressive force, so then compressive stress will induce in that, then the magnitude of the compressive stress can be given by P by A again, where P is the applied compressive load and A is the normal cross-sectional area of the section. So then P by A will give you the induced stress value. Now we'll take this induced stress value and we'll compare this one to the allowable compressive strength. Here sigma C is nothing but the allowable compressive strength of the material divided by the factor of safety. So that is the design equation when the component is subjected to a compressive stress. So that's what written here, where P is the external load, A is the cross-sectional area of the component, sigma and sigma C are allowable tensile and compressive stresses of the materials. So if you use something like within the bracket means, this is a notation what we are going to follow for the allowable strength. Then you have another kind of stress which we'll call it as a shear stress. So here what is the difference is, in case of normal stress always the loading is perpendicular to the cross section, whereas in case of shear stress the loading is tangential to the given cross section. When the external load acting on the component which tends to slide the adjacent planes with respect to each other, the resulting stress on this plane is called a direct shear stress. Why? Okay, here you remember this. There are different kinds of shear stresses. That's why here first we consider direct shear stress. Direct shear stress means when the load acting on the component will tend to slide the planes against each other. Suppose if I applied a force something like this for this component. Here if I consider at the center, so because of this load, bottom load, this layer will try to move in this direction. So and because of this load, it will try to move in this direction. So that means there is a relative sliding between these two layers. So because of that, the upper portion will move to this side and lower portion will move to this side, left side. So that means because of that, there may be a failure here. So if that kind of failure, then we'll call it as a shear failure. So if the stress induced because of this kind of action, we'll call it as a direct shear stress. So now if that is the case, so the same thing here. So here some riveted joint, lap joint is taken here. A lap joint is nothing but two plates placed one upon other. They are connected through some rivet here, and the joint is subjected to some force here. The force is applied to the plates. So now this plate will try to move in this direction because of the applied force, and this plate will try to move in this direction. Then at the junction of this rivet here, at this location, what happens is top portion of the rivet will slide in this direction and bottom portion of the rivet will slide in this direction. Because of that, here the rivet may going to fail something like this. You can see here, it will become into two halves here. One side the resistance of the material is in this direction. The other side it is in this direction. They are opposite. So because of this opposite resisting forces generated in the component, there will be relative sliding between the things. So therefore, it is going to fail something like this. So this kind of failure, what we'll call it as a shear failure, and the stress induced here in this phenomena, what we'll call it as a shear stress. and the magnitude of the shear stress is again, shear stress is denoted by the letters tau. So tau is given by the load applied divided by the shearing area. So you need to consider shearing area. So some you may come across sometimes we'll use we'll call it as a single shear or double shear, something like that. So that means in how many locations the shearing is taking place. If the shearing takes place only at one location, we'll call it as a single shear. If the shearing is taking place in two locations, then I call it as double shear. And similarly, maybe more than two also you may have, two locations also you may have, depending upon the connections. You may have more than two also. In that case, you need to consider those many number of times the shear strength values. So now here the design equation for this is the average stress is given by tau, that is nothing but the load divided by the shearing area. So whether it is in single shear or double shear, if double shear you need to take 2 times the shearing area. If it is a single shear, you have to take only A. So then again P by A, where P is the applied force and A is the shearing area. So here you are seeing the same letter A for the area, but these areas are not same and compared to the previous one. Previous one is the normal area, normal cross section area. Here it is the shearing area. So you need to make sure that the distinction between these two. So this should be equal or less than or equal to the allowable shear strength of the material. So now we know yield strength, we know ultimate tensile strength, but what is the allowable shear strength? How I can calculate that? So this ultimate shear strength will come from the experiment again. So what you will conduct in our MOS lab, some tensile test carried out, I think. So if you recall those principles from the tensile test, we can calculate the shear strength of the component also, provided your component is a ductile material. I'll tell you how to do that in the coming classes also. How we can estimate the shear strength of the component also. That we'll discuss in coming classes. But the time being, the design equation for this is your induced stress or average stress is, first the component should be safe, it should be less than or equal to the allowable strength or allowable stress of the material. Here, because it is shear stress, you need to consider shear strength. If it is a normal stress, you need to consider the tensile strength. If it is a shear stress, you need to consider shear strength only. Then you have bending stress. So when a component, suppose I have some shaft or a bar or a beam, let us say in case of bending, generally we'll call it as a beam. I have a beam having a circular cross section which is subjected to some end moments. So here the end moment is MO. So because of this end moment, the stresses will produce in this beam, but this is not a normal tensile stress or normal compressive stress, because in normal tensile or compression, we have only either tensile stress or compressive stress. Whereas in case of this bending, you have both. One side you have a compressive stress, other side you have a tensile stress. So depending upon the direction of this applied bending moment, if we reverse this direction of the bending moment, this will also reverse. So now you have here, top side you have a tension and bottom side has a compression if you reverse the bending moment. But both will exist here, and also not only that, the stress is not constant throughout the cross section of the beam. So in case of bending, the stress is varying linearly. So at some location there won't be any stress at all. That point or that layer, we'll call it as a neutral layer, where the strain or stress is 0. Then above the neutral layer you may have tension, or below the neutral layer you may have a compression depending upon the load. So in this diagram, here you have a compressive stress and the above the neutral layer, and a tensile stress below the neutral layer or neutral axis. You can say neutral layer or neutral axis is nothing but an axis which is drawn through the centroids of all those neutral layers. We call it as a neutral axis. So now above or below the neutral axis, there may be the signs are opposite for the stress. Of course, these are normal stresses only, but here it is the signs are different. One is in the positive direction, other one is in the negative direction. That means one is tend to elongate, another one is tend to compress the component. So therefore, in case of bending stress, even though you have two types of stresses, that is tensile and compression is induced, for design criteria will take the maximum value only. So that means whether you need to consider the maximum tensile stress or maximum compressive stress. You need to look at into the magnitude of these two. Then based on the magnitude, so if the value of the compressive stress is more compared to the tension, then I'll take the compressive stress as the induced stress value. Then I'll compare this one to the strength of the material to find the or to take it as a design equation to consider, I'll consider that one as the design equation. Or sometimes the tensile strength value, tensile stress is, if the tensile stress is more than the compressive stress, then I need to consider the tensile stress for the designing the component. So like that, in case of bending, even though you have two stresses, so far in case of tensile and shear stress, direct shear stress, you have only one value, but here you have two values. Out of these two, you have to consider the highest value. Don't bother about, disregard the magnet sign. That means whether it is negative or positive. Then generally we'll consider tensile is positive, compression is negative. So we don't bother about the sign here. The only thing is we need to consider whether it is tension or compression. Based on this, the magnitude will identify the largest stress value. So we'll take that largest individual stress value to compare the strength of the material so that you can design the component. So that's what written here. So now to calculate the bending stress, this is the formula. So the bending stress value sigma b is nothing but m into y divided by I. So I think all of you know about this equation. So where m is bending moment, y is the distance of the layer where you are considering, and the distance is measured from the neutral axis. Always this y is measured from the neutral axis. So therefore, if you know that if you move away from the neutral axis, the stress values will also increase. If you come closer to the neutral axis, it is going to decrease. Obviously, when y is equal to 0, that is nothing but neutral layer. At y is equal to 0, the stress is going to be 0. So that's why y is nothing but the distance of the layer where you are calculating the stress to the or from the neutral axis. You need to calculate that. Then I is the moment of inertia. So if you know all these things, bending moment and then moment of inertia, and then this bending moment of inertia will depend upon the cross section here. If you have rectangular cross section, you have one formula for bending moment. Not bending moment, area moment of inertia. What we call it as moment of inertia or area moment of inertia or second moment of inertia, whatever you call it as. So this is going to be for different cross sections. You have different formulas for that. I think all of you know those things also, because you might have studied this one in during your earlier mechanics courses, or maybe engineering mechanics, or maybe in this course also MOS1 and MOS2 also. You might have a lot of time, you might come across these high values. So there you have this bending stress also. Pure, here this kind of loading, what we call it as a pure bending or simple bending. So in case of simple bending, this is the formula to compute the bending stress. Then you need to take the magnitude of this bending stress and you need to equate that one to the allowable tensile strength or allowable compressive strength of the beam. Then from that you will get your desired dimensions. So where m is the applied bending moment, I is moment of inertia of the cross section about the neutral axis, and y is the distance of the fiber from the neutral axis. Then once you know about the bending stress, then you have torsal shear stress. So I think this is also a review only. You already derived these torsion equations, and also you know how to compute the torsal shear stress also. So this shear stress is also denoted by tau, but this is a torsional shear stress, not direct shear stress. It is different from that. So why it is different? In case of direct shear stress, the magnitude of direct shear stress is also uniform throughout the cross section. It is same. Whereas in case of this torsal shear stress, you can see this. If I take a circular shaft, if it is subjected to some twisting movement, mt, the twisting movement is taken as mt. So in that case, the expression of torsal shear stress is given by mt into r divided by j, where mt is the applied twisting moment, r is the again distance of the fiber from the neutral axis or from the centroid of the cross section. You need to measure this r. Then j is the polar moment of inertia. Here j is polar moment of inertia. Now if this r value changes, so now I need to measure that r from the centroidal axis of the cross section. If I go from the centroidal axis, so the r value will increase. At the centroidal axis, the r is going to be 0. So r0 means the torsal shear stress is 0. That means, that's why if you see, look at this diagram here. So at the center, it is 0. At the centroid, the torsal shear stress is 0, like your bending stress. In case of bending stress, you need to look at it the neutral layer, not the centroid. Of course, if the cross section is symmetrical, for most of the symmetrical sections, the centroid will coincide with the neutral axis. If there is unsymmetrical bending, then only the neutral layer or neutral axis will deviate from the centroidal axis. but in most of the cases for symmetrical sections, neutral axis will coincide with the centroidal axis also. Okay. So anyway, here at the centroidal axis, here the stress is 0. If you go away from that, it is increasing, and either side it is increasing. One side it is positive, other side it is negative here also. Only thing is, but the magnitude wise it is same on both sides. Magnitude is same on both sides. So that's why here you need to take R max value to compute the maximum shear stress value. Where now the difference here is, in case of partial shear stress, it is a variable stress across the cross section. It is going to vary from point to point in the section. Whereas in case of direct shear stress, it is not going to vary. So it is uniform throughout. So therefore here, since it is a variable stress, again here what you need to do is, you need to take the highest values or the magnitude of the largest stress. Then you need to equate that one largest value of the stress to the allowable shear strength of the material for design criteria. So this is how you can design when the component is subjected to, or this is how you can calculate when a component is subjected to a twisting domain. Similarly, you have a bearing stress or crushing stress. So we already discussed the bearing stress or crushing stress is nothing but whenever there is a relative displacement between two components. So then this is happened because of the pressurizing or squeezing the one component against each other. So therefore it will call it as the stress induced because of this pressurization or squeezing of the component, one component over the other. We'll call it as a bearing stress or crushing stress. And this bearing stress and crushing stress is okay, defined. This is the definition. Again, it is going to be always, it is going to be a compressive stress only. Bearing stress is always, it is compressive stress, and it is developed at the surface of contact between two interacting members that are relatively at rest. So when two components are relatively in rest position, because of the compressive action of the loading at the interface of these two surfaces, this stress will induce, and we generally will assume this crushing stress or bearing stress which is uniform throughout the cross section. Then, and also the magnitude of the stress can be calculated based on the projected area of the crushing area, projected crushing area. So now I have two examples here. One is like we already seen here in case of the lap joint, we already seen that this rivet is subjected to a direct shear stress here because of this applied force. Not only that, here, since this component and this component is having some, even though they are in equilibrium, there is some sliding is taking place at the adjacent of these rivets. So here, so this sliding or this squeezing, what I can say, instead of sliding, I can say it is pressurization or squeezing of this rivet. If the component, if this bottom plate moves like this and this top plate will move like this, so in addition to the EF shear, if you look at this surface and this surface, or how do you say this, the outer surface of the rivet is subjected to some sort of compression. So that's what shown here in the arrows here. So this compression will create the squeezing effect. So because of that, what happens is, around the circumference of the rivet, the material will come out in the form of a small fragment. So then the component may fail. So that kind of failure, what we call it as a crushing failure. So in that case, the magnitude of the crushing stress can be calculated by the load, which is P. Here the applied force is P, divided by the crushing area or the projecting area. Projecting area is nothing but the surface area of the rivet. So that is nothing but D is the diameter and the T is the thickness of the rivet. If that is the case, dt is going to be the projected area. So like that, not only this you may have another kind of example, that is bearings. So whenever shaft is there, and this is the bearing, hydrostatic bearing or hydrodynamic, whatever it may be, what kind of bearing it may be. So now here, this interface between the bearing and the shaft. So here, this interface is subjected to some sort of crushing. So because of the applied load. So now, because of that, the bearing pressure is going to create a stress at this interface. The stress what will call it as a crushing stress. Again here, we need to take this length multiplied by the diameter as the projected area, and then the load, whatever it may be subjected to, that load will call it as the applied load. So then that load divided by this project area will get the expression for the bearing stress or crushing stress. So here P bearing is not P. Okay, here it may be wrong. Here it's not P. It should be sigma here. Sigma bearing is nothing but load divided by the projected area. Load is P. Projected area is L into D. Where L is the length of the shaft or the portion of the shaft which is enclosed within the bearing. So only you need to consider this length, not the total length of the shaft. Only you have to consider this length. So that's why this is shown as L here. So here you can say this the L is not the length of the shaft, it is length of the bearing. L is the length of the bearing and D is the diameter of the shaft. So now if it is a static, you can say it is uniform. Suppose if it is a hydrodynamic, if it is a dynamic, in that case the stress is going to vary something like this. It is not uniform. But generally what we will do is for all our design criteria, in case of static loading, we will assume this stress is also, this one is also uniform. Even though it is not uniform, we will assume it is uniform and we will design the component. Then finally you have thermal stresses. So that means whenever a material is subjected to a temperature change, so it will try to expand or contract. Depending upon if the temperature increases, the material will try to expand. If the temperature, surrounding temperature decreases, the material will try to contract. So then, if this contraction or expansion is arrested, if this, what I can call, we will call it as a free expansion. That means, if I leave the component freely, then if the temperature increases, it will expand. If the temperature decreases, it will contract. So then, whatever may be the expansion or contraction, we call it as a free expansion or free contraction. If this free expansion is allowed in the material, then there is no issue, no stresses will induce. But if this free expansion is constrained or restricted, then because of that, thermal loads will induce and the thermal load will create a stress. We will call it as a thermal stress. Again, this thermal stress may be normal. Most of the cases, thermal stresses are nothing but a normal stresses only. Because of thermal load, shear stresses are not going to induce. Only the normal stresses are going to induce in the component. Why it is? Because I am restricting the expansion or contraction. Because I am expanding the expansion or contraction. Expansion or contraction is because of tensile or compressive load only. So therefore, always the thermal stress, the nature of stress may be either it may be a tensile stress or compressive stress. Always it is either a normal stress. It is not always, it is not going to be a shear stress. It is going to be only normal stress. So now, once you have a magnitude of thermal stress based on the material properties, that is alpha value, that is the coefficient of linear expansion, and what is the temperature change. So then what is the length of the component? You can calculate the thermal stress based on thermal strain. This is the formula for thermal strain, L alpha T by L, which is nothing but alpha T is the thermal strain. Once you know the thermal strain value, then using Hooke's law, you can calculate thermal stress value based on Hooke's law. That is, stress is directly proportional to strain and the proportionality constant is Young's modulus. Your sigma is equal to E epsilon. So then you will get a stress value. Then you need to compare the stress value against the yield strength. If it is a ductile material, you need to consider it as a yield strength. If it is a brittle material, you need to consider the ultimate strength. Of course, if you use factor of safety, you need to consider the factor of safety also. But here the sigma is the allowable stress. Whether you are following factor of safety or not, that is a different issue. If you follow it, you need to consider while calculating the allowable stress itself. Okay, so this is how you can design, or this is the design equation when there are thermal loads. Okay, so these are some fundamental basics how you can compute the individual stresses when you have a different kinds of loads. Suppose if you have a direct load, how you can compute the stress. If you have a direct normal load or direct shear load, we have seen the formulas how we can compute the stress values. Similarly, if the component is subjected to some sort of bending moment, then we know the formula how to compute the bending stress. Similarly, if a component is subjected to some sort of twisting moment, we know how to compute the torsional shear stress. When the component is subjected to a bearing pressure, then we know how to calculate the bearing stress or crushing stress. Now, if the component is subjected to some thermal stress or thermal loads, then we know how to compute the stresses values. So now, once you know all these things, then you are in a position to design the component when it is subjected to only simple load or when it is subjected to a simple stresses. So now we are in a position to design the component. So now I think today I will stop at this point. maybe in the next coming classes, we'll see how we can design the components based on the discussion so far, what we have done so far. That means when it is subjected to simple loads, how I can design the component. That we'll see in the coming classes. So today I will stop at this point. Then if you have any doubt, so then we'll discuss your doubts. So then we'll close the class. If you have any doubt, then you can ask now. So this is basically it is a review only. So review what you learned in whatever previous mechanics of solid course or engineering mechanics course. I not teaching anything new today. So it is already you studied. Just I reviewed what you already studied in the previous courses. Anyway, still you have any doubt, then we'll discuss. So I think so many people are already leaving, meaning that they know everything or they don't know anything. Okay, anyway, that is not an issue. So if you have any doubt, then you can ask. Otherwise,
Sir.
Yes. Yeah.
సార్ ఇందాక 317 పిలిచారంట సార్.
ఏంటి?
ఇందాక 317 సార్, 317 ఇందాక పిలిచారంట సార్. అంటే నేను ఇది తాతయ్యకి బాగోకపోతే డాక్టర్ వచ్చాడు సార్. సో నేను వేరే రూమ్ లో ఫోన్ పెట్టేశాను, నాకు తెలియదు సార్. వచ్చేపాటికి లెఫ్ట్ అయిపోయి ఉన్నాను సార్.
అవును, నువ్వు ఫోన్ ఆన్ చేసి ఎందుకు వెళ్ళావు? నువ్వు క్లాస్ అటెండ్ అవునోడి ఫోన్ ఎందుకు ఆన్ చేసి వెళ్ళావు?
క్లాస్ లోకి వచ్చాకే డాక్టర్ వచ్చారు సార్. అండ్ పక్క రూమ్ లోకి వెళ్ళాను, ఈ రూమ్ లో ఫోన్ ఉంది. నేను వచ్చేపాటికి లెఫ్ట్ అయిపోయి ఉన్నా, ఫ్రెండ్ చెప్పాడు సార్. మెసేజెస్ ఉన్నాయి వచ్చేపాటికి ఇలా పిలిచారని చెప్పారు సార్. మళ్ళీ లాగిన్ అయ్యాను.
అట్లాగా నాకేమనుకుంటా, నేను నువ్వు క్లాస్ లో ఉన్నావా లేదా నీ నెంబర్
అంతే సార్, అంతే సార్, అది కరెక్టే సార్.
2 minutes టైం ఇచ్చి
నా బ్యాడ్ లక్ ఏంటంటే కరెక్ట్ టైంకి మీరు చేశారు. అదే సార్, నేను వచ్చిందే 5 minutes, మీరు పిలిచిన తర్వాత వస్తే లెఫ్ట్ అయిపోయి ఉన్నాను. ఫ్రెండ్స్ మెసేజ్ చేసి ఉన్నారు సార్ అప్పటికే.
ఆ మెసేజ్ చేస్తే అప్పుడు ఫోన్ లో చూసుకుని అరే నేను పిలిచాడంటే అప్పుడు వచ్చి నువ్వు నాకు కహాని చెప్తాను.
వచ్చేపాటికి లెఫ్ట్ అయిపోయి ఉన్నా, ఏంటో అర్థం కాలేదు. వాట్సాప్ లో మెసేజ్ ఉంది, ఇలా సార్ పిలిచారు నిన్ను అని. లాగిన్ అయ్యాను సార్.
ఎవరు పెట్టాడు నీకు మెసేజ్? సార్ నేను పిలిచాడని నీకు ఎవడు మెసేజ్ పెట్టాడు
సార్?